Advanced Engineering Physics. Unit 1. Crystallography and Materials Characterization. Concept of nanomaterials. In the previous topics, we studied crystals, crystal structures, defects, and the arrangement of atoms in solids. All these discussions mainly dealt with bulk materials, where the dimensions of the material are large enough that their properties remain almost constant. However, when the size of a material is reduced to extremely small dimensions, typically between 1 and 100 nanometers, its behavior changes dramatically. Materials in this size range are called nanomaterials. A nanometer is 1/1000th of a meter. To understand how small this is, consider that a human hair is about 80,000 to 100,000 nanometers thick. Therefore, nanomaterials exist at a scale where the behavior of atoms and electrons becomes very different from that observed in ordinary materials. Nanotechnology is the branch of science and engineering that deals with the study, fabrication, and application of these nanometer-sized materials. The unique feature of nanomaterials is that they exhibit physical, electrical, magnetic, chemical, and optical properties that are often completely different from those of the same material in bulk form. For example, gold in bulk form appears yellow and chemically stable, but when gold is converted into nanoparticles, its color changes to red or purple depending on the particle size, and its chemical reactivity increases significantly. Similarly, materials that are insulators in bulk form may become conductive at the nanoscale, and materials that are normally non-magnetic may exhibit magnetic behavior. The origin of these unusual properties lies mainly in two factors. The first is the large surface-to-volume ratio. The second is quantum confinement. Let us first understand how nanostructures are classified. Nanostructures are classified based on how many dimensions are confined to the nanometer scale. If a material is confined in only one dimension and is free to extend in the other two dimensions, it is called a two-dimensional nanostructure. Thin films are examples of this category. If a material is confined in 2 dimensions and can extend only along one direction, it is called a one-dimensional nanostructure. Examples include nanowires, carbon nanotubes, and conducting polymers. A carbon nanotube is essentially a cylindrical sheet of carbon atoms with a diameter of only a few nanometers, but a length that can be thousands of times larger. Similarly, nanowires are extremely thin wires through which electrons can move primarily in one direction. If a material is confined in all 3 spatial dimensions, it is called a zero-dimensional nanostructure. Examples include metal nanoparticles, semiconductor nanocrystals, and quantum dots. Since these structures are confined in every direction, their energy levels become discrete, much like those of isolated atoms. For this reason, quantum dots are often called artificial atoms. The classification of nanostructures, based on dimensionality, helps us understand how electrons behave in these systems and why their properties differ from bulk materials. Now, let us discuss one of the most important reasons behind the unusual behavior of nanomaterials, namely the surface-to-volume ratio. In a bulk material, most atoms are located inside the material. Only a small fraction of atoms are present on the surface. The interior atoms are completely surrounded by neighboring atoms and are therefore strongly bonded. As a result, the surface contributes very little to the overall properties of the material. However, as the size of the material decreases, the fraction of atoms located on the surface increases dramatically. In nanoparticles, a large percentage of atoms are present at the surface rather than inside the material. This changes the physical and chemical properties significantly. For a spherical nanoparticle having radius r and average atomic spacing a, the ratio of the number of surface atoms to the total number of atoms is given by n surface divided by n equals 3, a divided by r. This equation shows that the fraction of surface atoms is inversely proportional to the radius of the particle. As the radius decreases, the surface-to-volume ratio increases rapidly. Let us consider an example. Suppose the radius of a nanoparticle is 6 times the atomic spacing. That is, R equals 6a. Substituting this value into the equation gives n surface divided by n equals 3, a divided by 6a. This simplifies to 1 by 2. Therefore, 50% of all atoms are located on the surface. This means that half of the atoms in a nanoparticle are exposed directly to the environment. Such a large number of surface atoms has profound consequences. The first consequence is a reduction in melting point. Surface atoms are not completely surrounded by neighboring atoms. Therefore, they experience weaker bonding compared to atoms in the interior. As a result, less energy is required to separate these atoms. Consequently, nanoparticles melt at temperatures much lower than the melting temperature of the corresponding bulk material. For example, gold nanoparticles melt at temperatures significantly below the melting point of bulk gold. The second consequence is increased chemical reactivity. Since a large number of atoms are exposed on the surface, nanoparticles provide more active sites for chemical reactions. Therefore, they are highly effective catalysts. Catalysts increase the rate of chemical reactions without themselves being consumed. Nanoparticles are widely used as catalysts in industries because their large surface area greatly enhances reaction efficiency. The high surface area also makes nanomaterials useful for gas storage, sensors, batteries, and environmental purification. Thus, the large surface-to-volume ratio is one of the key reasons why nanomaterials behave differently from bulk materials. Now, let us discuss the second important factor, namely quantum confinement. In bulk materials, electrons can move freely over large distances. Their energy values form continuous bands. This means electrons can possess a wide range of energies. However, when the size of the material becomes comparable to the wavelength of electrons, the motion of electrons becomes restricted. This phenomenon is called quantum confinement. Quantum confinement causes the energy levels of electrons to become discrete instead of continuous. As a result, the electrical and optical properties of the material change significantly. Let us first consider one-dimensional nanostructures such as quantum wires and carbon nanotubes. In these systems, electrons are confined in 2 directions, but can move freely along the 3rd direction. Therefore, electron motion is restricted in the x and y directions while remaining free along the z direction. This confinement leads to the formation of one-dimensional energy subbands. The density of electronic states in these systems is not smooth. Instead, it exhibits sharp peaks at specific energies. These peaks are known as Van Hove singularities. A Van Hove singularity is a point where the density of states increases sharply and theoretically becomes infinite. These singularities strongly influence the optical absorption, emission, and electrical conductivity of one-dimensional nanostructures. For example, the unique electronic properties of carbon nanotubes arise because of these sharp peaks in the density of states. Now, let us move to zero-dimensional nanostructures, namely quantum dots. Quantum dots are tiny semiconductor crystals in which electrons are confined in all 3 spatial dimensions. Since electrons cannot move freely in any direction, they can occupy only specific energy levels. Thus, quantum dots have discrete energy states similar to atoms. That is why they are often called artificial atoms. The energy levels of electrons in a spherical quantum dot are given by the equation ENL equals h cross squared multiplied by alpha NL squared divided by 2m star r squared. In this equation, h cross is the reduced Planck constant, m star is the effective mass of the electron, alpha NL is a constant related to the allowed quantum states, and r is the radius of the quantum dot. The important point to note is that energy is inversely proportional to r squared. This means that when the radius decreases, the energy increases rapidly. Consequently, the energy gap between the valence band and the conduction band becomes larger as the size of the quantum dot decreases. This phenomenon is known as bandgap tuning. Bandgap tuning is one of the most remarkable properties of semiconductor nanocrystals. By simply changing the size of the quantum dot, we can change its optical properties. For example, cadmium selenide quantum dots emit different colors depending on their size. Larger quantum dots emit red light because they have a smaller band gap. Smaller quantum dots emit blue light because they have a larger band gap. Thus, by controlling the size of the nanoparticles, scientists can precisely control the color of light emitted by them. This property has revolutionized many technologies. Quantum dots are used in high-definition television displays, light-emitting diodes, lasers, biological imaging, fluorescent labels, and solar cells. Their brightness, color purity, and tunable emission make them extremely valuable in modern science and technology. To summarize, nanomaterials are materials having dimensions in the range of 1 to 100 nanometers. Their properties differ greatly from bulk materials because of two important reasons. The first is the enormous surface-to-volume ratio, which increases chemical reactivity and lowers melting point. The second is quantum confinement, which causes the energy levels of electrons to become discrete and allows the electrical and optical properties to be tuned by changing the size of the material. One-dimensional nanostructures, such as nanowires and carbon nanotubes, exhibit unique electronic behavior because of Van Hove singularities. Zero-dimensional nanostructures, such as quantum dots, possess atom-like discrete energy levels and exhibit size-dependent optical properties. These fascinating characteristics make nanomaterials one of the most important and rapidly developing areas of modern physics, materials science, electronics, medicine, and engineering.